Okay, so chapter 15, chemical equilibrium. In this chapter, we're going to study the chemical equilibrium. So first, we want to see the rate of a chemical reaction because when you have a chemical equilibrium, the rate of forward reaction and the reverse reaction are the same. So the rate of chemical reaction is a measure of how fast the reaction proceeds. It's defined as the amount of reactant that changes to product in a given period of time. Um, so in a chemical reaction with a fast rate, the reactants react to form product in a short period of time. And in a reaction with a slow rate, so the reactant react to form a product over a longer period of time. Um, in general, reaction rate depend on the nature of the reactant, which means what type of reaction or reactants we have. Reactant concentrations, the higher the concentration, the higher the rate. The temperature of the reaction, the higher the temperature, the higher the rate. The catalyst, so usually we will have the catalyst to increase the rate. So why that? Why those like on the last slide, those variables or the factors affecting our rate? Because there's some theory called the collision theory of chemical reactions. In a chemical reaction, or chemical reactions occur through collisions between molecules or atoms. If the collision occurs with enough energy, that is, if the colliding molecules are moving fast enough, the reaction can proceed to form the product. And in details also like depend on the location of the collision, which related to the orientation of the reactant. If the collision occurs with insufficient energy, the reactant molecule bounce off from one another without reacting. Since gas phase molecules have a wide distribution of velocity, collision occur with a wide range of energies. High energy collision leading to products, low energy collisions do not. So high energy collision are more likely to lead to products because most chemical reactions have an activation energy. So this activation energy, this word referring to this the red arrow or this green arrow, which is the energy difference between the reactants and then this is called the transition state. So this is called the activation energy. It's kind of a mountain or a barrier between the reactant product. So in order for the reactant to be converted to the product, those atoms, the reactant and have atoms, they must climb over this barrier. So the activation energy is an energy barrier that must be overcome for the reaction to proceed. The activation energy may be the energy required to begin to break the bonds of the reactants. Catalysts increase the rate of reaction by reducing the activation energy. See here the compare of two curve. The red curve is the chemical reaction without the catalyst. The green curve is the reaction with the catalyst. So we can see with the catalyst, the energy barrier getting lowered or the activation energy is reduced, so the reaction can be faster. If molecules react with high energy collision, then the factor that influence the rate of reaction must be the same factor that influence the number of high energy collisions that occur per unit of time. So the two most important factors are the concentration of the reactant molecule and the temperature of the reaction mixture. The rate of chemical reaction generally increases with increasing concentration of the reactants. The exact relationship between increases in concentration and increases in reaction rate varies for different reactions. and is the subject of a study in chemical kinetics. For example, here is the chemical reaction, H2 plus I2 produce 2HI, and so this reaction is one of those reactions that depend on the concentration of the reactant. And you can see if low initial concentration, that means slower initial rate. If we increase the concentration of the reactant, we can see the reaction rate increases, and then we see intermediate concentration, high concentration. So you can have this kind of comparison, or can see the relationship between the rate and the concentration. So those detailed words like the rate, initial rate, which is just referring to the rate right after you mix the reactant, and as the reaction goes on, then the rate will change. The rate will getting smaller and smaller because the concentration of the reactant getting lower and lower. So raising the temperature also make the molecule move faster. More collision occur per unit time, resulting in a faster reaction rate. A higher temperature resulting in more collision than are of that are of high energy. Since it is the high energy collision that result in products, this also produce a faster rate. So here again, we will compare the rate at different temperatures. So we have a low temperature, low rate, and intermediate temperature, intermediate rate, high temperature, fast rate. So here, those cartoons just try to show you by using this kind of image, there's a tail or shadow for those molecules. If they are moving faster, then the shadow or the tail is longer. So we can see the rate depend on that. So then what are the factors that influence the chemical reaction rate? We know the answer will be the nature of reactant, concentration, temperature, and catalyst. And also like the nature of the reactant means what kind of reactant we have, what are the state. So reaction rate generally increases with increasing reactant concentration, but not always. Some of the chemical reactions do not depend on the concentration. Rate generally increases with increasing temperature. Catalyst increase reaction rate. A reaction that can proceed in both the forward and reverse direction is a reversible reaction. So technically, every chemical reaction is reversible. In a chemical reaction, the condition in which the rate of forward reaction equals the rate of the reverse reaction is called dynamic equilibrium. But this condition is not static. If it is dynamic, which means the forward and reverse reaction are still occurring, but at the same rate. When dynamic equilibrium is reached, the concentrations of reactants and products no longer change. Even though the chemical reaction, the forward reaction, the backward reaction is still going on, but the concentration are not changing. The reactants and products are being depleted at the same rate at which they are being formed. Equilibrium, when the concentration of the reactants and products no longer change, the equilibrium has been reached. So here is another example we saw before, chemical reaction that is reversible. H2 plus I2 produce 2HI. And this reaction is reversible, so therefore we have the forward reaction going from H2 plus I2 produce HI. A reverse reaction will be the HI decomposing to H2 and I2. And see here are the few pictures show you those molecules, the reactant and the product at different time. So at time 0, we began this process is just one way to begin this process to get the equilibrium. In this example, is we only have the H2 and I2 of the reactant on the left. You can see in this picture. So then as the time goes on, let's say 15, maybe 15 seconds or 15 minutes, we have some of those products, which is the HI. So this larger blue and this white representing the HI. We see the HI already began to produce. So then, as more time goes on, we will see the more HI produced. Once we have the HI produced, then the reverse reaction began to happen. So therefore, at some time, you don't have to be the same number of HI, same number of I2, H2, so depend on how they affecting your rate. So at some time, the forward rate, the reverse rate are the same, then we see we have equilibrium. For example, in this case, we will see it happens, the equilibrium happens at 30 seconds, 30 minutes. Because after that, we see at 30 seconds, we have this ratio in this mixture. We have 4H2, 4I2, 8HI. And then even after some time, like 45 seconds, we can see we still have the same ratio. So therefore, we know after 30 seconds, for this example, it has established the equilibrium. So because at equilibrium, the concentration of the reactant and product no longer change, some type of constant. So therefore, we can quantify the relative concentrations of the reactants and product at equilibrium by using the equilibrium constant K sub EQ. So when dynamic equilibrium is reached, the forward reaction rate is the same as the reverse reaction rate. So from this principle, from this statement, we can get some of those equation for the KEQ. Because the reaction rate are the same, the concentration of the reactant product no longer change. The consistence of concentrations of reactant product at equilibrium does not imply that the concentrations of the reactant product are equal at one another at equilibrium. So this is very important. Yeah, we just know they are constant. We don't know for sure they are equal. We know the reaction rate are equal. The forward reaction, reverse reaction rate are equal. Some reactions reach equilibrium only after most of the reactants have formed the product, and vice versa. Other reactions reach equilibrium on only a few fraction of the reactant has been formed the product. The amount of reactant product depends on the reaction and can be expressed numerically by the equilibrium constant K sub EQ. So again, the equilibrium constant K sub EQ, consider the generical chemical reaction. So this is generical, we just use A, B, C, D to represent some of those substances in the chemical reaction, using the lowercase a, b, c, d to represent their coefficient. So in this equation, A and B are reactant, C and D are products, then lower A, B, C, D are the respective stoichiometric coefficient in the chemical equation. The equilibrium constant for the reaction is defined as the ratio at equilibrium of the concentrations of the product raised to their stoichiometric coefficient divided by the concentration of the reactant raised to their stoichiometric coefficient, which means mathematically, you see, you use the concentration of the product, then use their coefficient as the exponent, you multiply all the concentration for the product, then divided by all the similar way using the concentration of the reactant and their coefficient as the exponent, then multiply all those for the reactant, you have this ratio. This ratio will be the KEQ. So in details, shall we put everyone in the equation into this equation for KEQ? Well, in details depend on the state for those product and reactant like A, B, C, D. What are their state? The common state is solid, liquid, gas, and aqueous. So later on, we'll say we only put those substances that is in the gaseous state or in the aqueous state in this equation. Okay, so here is one example. We have a exactly particular example of chemical equilibrium, which has this N2O5 in gas, or two of that, because this equation needs to be balanced, and decompose into four of those NO2 in gas and then O2 in gas. This don't have number, that means this is one. So therefore, we were just using what we talk about. We see these are the two products. This is reactant. So we put the product on the top using coefficient as exponent, and we have all the three here because they are all in gas state. So notice that the coefficient in the balanced chemical equation become the exponent. Okay, so here the highlight, the red two is from the coefficient become the exponent, and this 4 is the coefficient become the exponent for this NO2. So that's how you write the chemical equilibrium constant equations. Only include the reactant and product in G means gas or AQ state in the equation for the KEQ. So again, here all the three substances they are all in gas, so therefore we including all the three here in the equation for the KEQ. If they are in the AQ state, which means aqueous, we also included them. If they are in the liquid or solid state, we will not put them in the equation for the KEQ. Okay, so the product on the top, reactant at the bottom. So then those has more than one product or more than one reactant. So this means we multiply them. All right, so then the significance of the equilibrium constant, we can use them to do some calculations. We can also use them just tell like qualitatively what they mean. So for example, if you have a KEQ that is relatively large, what I mean by large, we usually say larger than one. So that means it favors the product. So here's one example. We have H2 plus I2 plus 2 HBr and tell you at 25 degrees Celsius, the KEQ is 1.9 times 10 to the negative 10 to the positive 19. That means this reaction hugely favors this HBr. So there will be a high concentration of product and low concentration of reactant at equilibrium. When the KEQ is small, usually we say smaller than one, even though this number is really much larger than one, and some number will be much larger than smaller than one. So here is one example. This is much smaller than one because it's 10 to the negative 31. So that means this reaction pretty much do not proceed from left to right. You will have a lot of reactant left over or at equilibrium. So there will be a high concentration of reactant and low concentration of product at equilibrium. And so as we saw before, KEQ much smaller than one, reactant are favored, product are not favored. KEQ approximately equal to one. That means neither reactant nor product are favored. Significant amount of both reactant and product are present at equilibrium. If KEQ, so the two larger than sign means much larger than. So then the product are favored, reactant are not favored. So here we examine the details, the so-called heterogeneous equilibrium. The concentration, that means we will have some of those substances in the chemical equilibrium are in different states. So therefore, the concentrations of pure solid and pure liquid are excluded from equilibrium expression, which means the equation for the K sub EQ because they are constant. So the concentration for a pure substance and a pure pure substance, pure substance in solid and in liquid. So those concentration, they do not change. So here is one example of heterogeneous equilibrium. So we have a CO2 in gas, CaO in solid, CaCO3 in solid. So we follow our usual procedure. We will see I will write the CaOS and multiply by CO2 gas on the top, and then CaCO3 at the bottom. Now, because they are solid, so you just don't need to put them in your equation. You just replace them by one. If you forget initially write them there, then just simply change them to one, then you will get this answer. So since CaCO3 solid and CaOS are both solid, they are omitted. They are kind of they're like a contribution is replaced by that number one. So you multiply anything by one, divided by anything by one, still have the same. So here we have one example. I want to calculate equilibrium constant. So we have this equation written, which is balanced, which has the states. So all the three substances here are gas, this compound, these two elements. And then tell you at equilibrium, the concentration of these three, H2 is 0.11 molar, I2 is 0.11 molar, HI 0.78 molar. So by the way, when you calculate the KEQ, you can either use molarity or use pressure if they are gas. If you use molarity, which means concentration, or another way to say that is if you use concentration, you must use molarity. If you use pressure, you must use ATF. So for this question, we are given the concentration at equilibrium in molarity. We are given this equation, so you want to calculate the number for this P sub EQ. You just write the equation first. So what is the equation for this P sub EQ? So as usual, we'll write the product on top and use coefficient as the exponent. So here the coefficient 2, we use that 2 as the exponent. That way just divided by those concentration for the reactant. So here that means these two are both reactant, and we will multiply them in this denominator. So now we have the equation, we just plug those numbers in, and we have the concentration in molarity is must be in molarity, otherwise you have to convert. So the HI is 0.78 molar, you don't have to write molar anymore, just make sure they are in molar. 0.78 squared, then you divide by this concentration of H2, 0.11, then multiply by the concentration of I2, again, 0.11. Just use the calculator to calculate, so get like 50, but you want to show that in scientific notation, just 5.0 10 to the positive 1. Right. So now you can also using that equation, the KEQ, to do something else. So in this example, you are given at equilibrium the concentration of this reactant, and then the concentration of this product. Also give the K sub EQ, the number for the K sub EQ. So now ask you to calculate this other product CO2 at equilibrium. So you do just similar as in the last slide, you just first write the equation for the K sub EQ. So then you're solving this equation for what you want to calculate. You want to calculate this CO2 at equilibrium. So you multiply this over, then you divide that out. So therefore you get this equation. So then you just plug in. So you are given this KEQ 2.00, and you are given the concentration of COF2. So COF2 0.255. So put it here, the square come from the coefficient of COF2, and then you divide by this CF4 concentration at equilibrium, which is 0.118. So there are these three numbers. So use your calculator, you get 1.10, which means this 1.10 capital M, a molarity, is the concentration of CO2 at equilibrium in this setting. So we are also doing some of those qualitative analysis. see what will happen to the equilibrium if we disturb the equilibrium. And this was really long time ago summarized by the Li Xiaolai. So therefore, we have the Li Xiaolai principle, which said when a chemical system at equilibrium is disturbed, the system shift in a direction that try to minimize the disturbance. For example, disturb a system by adding product if the product is in gas or aqueous state. And here is the one example. We have the product reactant and both of them in gas state. So if you add in the product, you actually try to minimize this disturbance, which means try to reduce the product shifting to the left. So if you again just using this, so we are adding this NO2, which is on the right side of this equilibrium sign. If you add and this chemical equilibrium, try to minimize your disturbance. If you adding on, if those are in gas or in solution aqueous state, that will really become a disturbance. So therefore, it will shift to the left. Try to use the NO2 and so therefore, when a system at equilibrium, which means chemical equilibrium system chemical reaction, called system, when a system at equilibrium is disturbed, it changes to minimize the disturbance. So adding NO2 this disturbance, because this is the gas, cause the reaction to shift left, consuming NO2 by form N2O4. When again this is the Xiaolai principle, so we saw that before. So we see another example by adding a reactant. Let's see the same reaction. We have N2O4 and NO2. So now we see we want to add in N2O4. N2O4 is in gaseous state. So this is the disturbance. That means your reaction will shift to the right to use up the N2O4 and produce NO2. Okay, so when a system at equilibrium is disturbed, it changes to minimize the disturbance, adding N2O4 the disturbance causes reaction to shift right, consuming N2O4 by forming more NO2. Now, there are some other disturbance. So one other disturbance is the change in the volume of reaction. If the reaction has gas, and it will be a disturbance. So change the volume of a gas or a gas mixture result in change in pressure. We have to know that how that's related. So a decrease in volume causes an increase in pressure. This is Boyle's law, and an increase in volume causes a decrease in pressure. So from the ideal gas law, we know PV equals nRT. We can see that lowering the number of moles of gas resulting in a lower pressure at a constant temperature and volume. So therefore, a system can respond to a disturbance by changing the moles of gas present to relieve pressure change. And here I show you the Boyle's law. So when a volume of an equilibrium mixture decreases, the pressure increases, right? So that's kind of common sense. When you have a piston, and if you decrease the volume, then the pressure increases inside the piston. Well, obviously, we're assuming the temperature is not changing, how much gas in the piston are not changing. So that will be true. That can happen. So decrease in volume cause increase in pressure. And now we're going to use this to study this chemical equilibrium. In this chemical equilibrium, we have N2 gas plus 3 H2 gas produce 2 NH3 gas. And here the pictures. So all together, we see how much more of gas on the left and how much more of gas on the right. Why we do that? Because we're treating those gas as ideal gas. And when we think of the gas are ideal so their pressure only depend on how much we have. I mean, again, constant temperature. So therefore we don't care are they N2 or H2. We just see how much together they have. So we have 4. This 4 comes from this coefficient 3 here, plus this 1 here. So 3 plus 1 is 4. And here is 2. 2 comes from this coefficient. So we just compare how many moles by adding the gaseous coefficient on the left, on the right. So in this particular example, we compare like 4 mole of gas with 2 mole of gas, left and right. So therefore, if we decrease the volume, and so your chemical equation, chemical equilibrium, try to do something to release your disturbance. So as we analyze in this picture, we can see if we decrease the volume, the pressure increases. So then how can the chemical equilibrium reduce the pressure? It can reduce the pressure by shifting to a side that has less gas, because we saw on last slide, so the pressure kind of proportional to how much gas it has, which in our last slide showed by that variable n, or the number of moles of gas. Okay, so again, the system responds to bring the pressure back down by shifting to the right for this particular reaction, the side of reaction with the fewer moles of gas particles. And reversely or oppositely, if you increase the volume, then the pressure will decrease. When the volume of equilibrium mixture increases, the pressure decreases. We are again using this equilibrium N1 N2 gas plus 3 H2 gas produce 2 and H3 gas. So now we'll see what will happen if we increase the volume, which side it was shifting. We were counting all together how many more of gas on the left, how many more of gas on the right. We're just adding those substances in the chemical equilibrium, or adding those coefficients of the substances in chemical equilibrium which are in the gas state. So here they are all in gas state, so therefore we're just adding their coefficient 1 and 3, adding equal to 4. So here is 2. If you increase the volume, your reaction will shift to the left because the chemical equilibrium try to counter or do something against the disturbance. So if the disturbance is the decreasing pressure, the equilibrium or the chemical equation try to increase the pressure by producing more gas. So when this equilibrium shifting from right to left, it will using some gas but producing more gas. So the net change, if you shift to the left, there will be more gas. To summarize, if a chemical equilibrium is at equilibrium, the effects of volume change are as follows. Decrease the volume causes the reaction to shift in the direction that has fewer moles of gas particles, maybe right, maybe left, depending on your chemical equation. In the last example, we see the shifting to the right. So oppositely, increasing the volume causes the reaction to shift in the direction that has more moles of gas particles. Notice that if a chemical reaction has an equal number of moles of gas particles on both sides of the chemical equation, a change in volume has no effect. Or if your chemical reaction don't have any gas in the equilibrium, then it's also change the volume will not change or not shifting the equilibrium. So some of those very interesting is the chemistry and the health. How a developing fetus get oxygen from its mother. We will see the hemoglobin is in work. Well, hemoglobin for the adults and for the fetus are little different. So hemoglobin, we just see HB react with oxygen according to the equilibrium equation as see here. So every one hemoglobin can carry one O2 molecule. This is just one example. The equilibrium constant for this reaction is neither large nor small. Consequently, the reaction shifting towards the right or left depending on the concentration of the oxygen. As blood flows through the lung, where oxygen concentration are high, the equilibrium shifting to the right, hemoglobin loses oxygen. So as blood flows through muscles and organs, they are using oxygen in those places. Oxygen concentration have been depleted. The equilibrium shifting to the left, which means the hemoglobin release oxygen, like adult hemoglobin, fetal hemoglobin is also in equilibrium with oxygen. So here we see this, we use HbF representing the hemoglobin for those fetus. And so they are a little different than the adults hemoglobin. So the fetal hemoglobin HbF is slightly different from the adult's hemoglobin. The equilibrium constant for fetal hemoglobin is larger than the equilibrium constant for adult hemoglobin. That means the fetal hemoglobin will load oxygen at lower oxygen concentration than adults. So that kind of grab away those oxygen from the baby mother's blood. So when the mother's hemoglobin flows through the placenta, it unloads oxygen into the placenta. Nature has this engineered chemical system in which the mother's hemoglobin can, in effect, hand off oxygen to the baby's hemoglobin. Next, we will examine the effect of temperature change on equilibrium. So in a chemical reaction, the heat may be absorbed or released. So therefore, we have the exothermic reaction or endothermic reaction. In an exothermic reaction, we can think of heat as a product, which means exothermic reaction releasing heat. So therefore, rising the temperature of an exothermic reaction, so think of this as adding heat to the product side, causing the reaction shifting to the left of the reactant, or left to the reactant. So in an endothermic reaction, we can think of heat as a reactant. Raising the temperature of an endothermic reaction, thinking of this as adding heat to the reactant side causes the reaction to shift right to the product side. So again, this is a generic equation. We use A, B, C, D. So if the reaction is exo, we will write here the heat on the right side, which means the product side. If there's one example that is the exothermic, we saw this reaction before. It's N2 H2 produce NH3, which is very useful reaction. So this reaction is exo. Then we will see this heat. We write the heat here. So now we are thinking of what do we do to the heat? If we adding heat or we reduce heat. Usually we see we adding heat is by increasing the temperature of the reaction mixture. So if we adding heat and we were treating this heat as a product in the gas or aqueous state, therefore it is shifting this to the left. And so we can either adding or take away. So if we take it away, which means we decrease the temperature of this reaction, so then your reaction try to make up for what it did. If you remove heat, it try to produce heat by shifting to the right. And for the endothermic reaction, we're still using the same generic letter A, B, C, D. If what it told you is endo. So some way it will tell you it's endo or exo. So then you will write heat on the left. And this is a very interesting equilibrium because these two they have a different color. So N2O4 is colorless, NO2 is brown. So therefore, you can see visually in the laboratory whatever happened to this equilibrium if you adding heat or if you increase the temperature. If you increase the temperature, which means you adding heat, so make this reaction shift to the right. The right side is brown, then you will see the color become darker. And oppositely, if you take a heat away by reducing the temperature, which means you can have this equilibrium in a mixture. You put this mixture maybe in a test tube, or maybe in a beaker. Then you put this test tube in the ice bath. So you take a heat away, then it will shift to left. Then your mixture become like a lighter or kind of a colorless. Here is the picture. So we see here this and warm temperature or hot water, this cold temperature for this equilibrium, then this equilibrium is endo. So therefore, at hot temperature, we see this tube have this equilibrium. It become like a brown or kind of yellowish. If you do the opposite, adding this tube or take this tube to an ice bath, so this equation shifting to the left side is the colorless. So that's how we see the temperature change for some reaction. Visually, we saw that. And to summarize, so in an exothermic chemical reaction, heat is the product, and the effect of temperature change as follows. Increased temperature causes reactions to shift left in the direction of the reactant. Decreased temperature causes the reaction to shift right in the direction of the product. And then in an endothermic chemical reaction, heat is a reactant, and the effect of temperature change are as follows. Increasing the temperature causes the reaction to shift right in the direction of the product. Decreasing the temperature causes the reaction to shift left in the direction of the reactant. And solubility is also an equilibrium process. So the process by which an ionic compound dissolves is an equilibrium process. The equilibrium expression for the chemical equation that represent the dissolving of an ionic compound is the solubility product constant. So we shall use K to represent the equilibrium constant. Then this equilibrium process has a special name called solubility. So therefore, we have this special notation for this type of equilibrium process called the K sub SP. S comes from solubility, and P means product. Product means multiply. So solids are omitted from the equilibrium expression. A large K sub SP, the forward reaction favored means that the compound is very soluble. A small K sub SP, reverse reaction favored means that the compound is not very soluble. To write the expression for the K sub SP, first write the balanced chemical reaction equation showing the solid compound in equilibrium with its dissolved aqueous ion, then write the equilibrium expression based on this equation. So for example, if you have this ionic compound, calcium fluoride, which is CaF2 solid, as it dissolves in water, then it will dissociate or separate into ion in aqueous state. So from each one of this unit, we see one Ca, and we know Ca is a metal, it produces positive ion. So we see typically it will be 2+ ion. And from this subscript 2, that means we can produce 2 negative ions from the F. And we know fluorine is non-metal is group 7A. So typically F is -1 ion. And we get the 2 from this, so this equation is balanced. So now you have the equation, and you have the coefficient, you have the state, and then just don't write this solid in your equation for the K. So therefore, your equation for the KSP for this solubility process, it will be simply the product concentration, and then the exponent will be the coefficient. Don't forget the exponent, and the coefficient for Ca2 plus is 1. If 1, you don't have to write the exponent. Then the coefficient for F1 -2, so therefore you see this square here. Then this is the rectangle. So ideally you write that at bottom or the denominator, but because it's solid, so just replace that by 1. And so therefore we don't have the right 1 in the denominator. So that will be our final answer for the K sub SP for this example. And here just this table just show you different number for the K sub SP for different ionic compounds. You can see some of them is reasonable, not too small, like lead 2 chloride, 10 to -5. Even though still small, that means that's why we say they are insoluble. But they are different KSP. So now you can using the K sub SP from the last slide to calculate the molar solubility. What that means is you can see how much of the BeSO4 together in the concentration of molar, which is molarity, dissolve in water. So what you do, you will write this equation. So if you starting with BeSO4 solid, it will dissolve. If it dissolve, it will dissociate. So dissolve, dissociate are a different concept. So dissolve, that means it get into solvent, into water, then dissociate, it's kind of separate for the ionic compound. So we separate this into ion. We will see the Ba2 plus ion, SO4 2 negative ion. And the equation is balanced. The coefficient is 1 for everything. So now you write the equation for the KSP, right? Because you want to use the KSP to calculating molar solubility. So the KSP will be simply this. Now you will see if you define the molar solubility as dissolved BaSO4 at equilibrium, and then you will see if you dissolve S molarity of BaSO4. So we see S of this dissolve, and then we see as soon as this dissolve, or as much as this dissolve will produce same amount of Ba2 plus SO4 2 negative. So therefore, we will see the concentration at equilibrium of Ba2 plus SO4 2 negative is same as the molar solubility. So therefore, we have this information. We want to calculate the molar solubility S. So now we have this information here in this equation. So therefore, we will substitute the Ba2 plus SO4 2 negative, both of them by S. Then we use the table 15.2 to get a number for K sub SP. Okay, so again, you first just substitute Ba2 plus SO4 2 negative by the S, because from this reasoning, we see both of them are S. So S times S is S squared. But then you want to solve this equation for S, you will take the square root. So S equals the square root over K sub SP. Go to table 15.2, you see what is the KSP for the barium sulfate is 1.07 times 10 to -10. Take the square root of that. So therefore, we solve the problem. We see the solubility for barium sulfate is the molar solubility is 1.03 times 10 to the -5. So usually this referring to the room temperature, temperature about 25 degrees Celsius. Now we see the everyday chemistry, the hard water. So because of their relatively low solubility product constant, water can easily become saturated with calcium carbonate and magnesium carbonate. A drop of water becomes saturated with calcium carbonate and magnesium carbonate as the water evaporates. So a saturated solution such as this precipitate some of its dissolved ions. And so this precipitate show up as scaly deposits on faucet, sink, and cookware, causing cars or dishes with hot water leaves a spot of calcium carbonate and magnesium carbonate as the solid precipitate out of the driving drops of water. The equilibrium constant describes how far a chemical reaction will go. The reaction rate describes how fast it will get there. So the activation energy or activation barrier for a reaction is the energy barrier that must be overcome in order for the reaction for the reactants to be converted into product. Activation energy exists for most chemical reactions because the original chemical bond must begin to break before new chemical bond begin to form, and this requires energy. Again, this picture shows you the energy diagram for a chemical reaction. So we have the vertical axis are the energy. We don't have an absolute unit, just relatively speaking. And then this horizontal axis just show you the process of the chemical reaction, which means do you have a product, do you have a reactant, or what are where is your chemical reaction? So this is starting with your reactant. We don't have a reaction yet, then we will see this much of energy for all these atoms in your reactant. If you want to converting all those reactant or those reactant into products, so we have to go through some of this chemical process to break some of those chemical bonds to produce new chemical bonds. So therefore, we will see this is like 6 atom. So somehow they have to climb over this barrier by breaking the O bond. So therefore, this two-head arrow indicate the energy difference between the energy of the reactant and this highest point here. So this is so-called activation energy. Okay, so are there any way to speed up a slow reaction, one with a higher activation energy barrier? I saw you do that before, right? So a chemical reaction, for a chemical reaction, the higher the activation energy, the fewer the number of reactant molecules that make it over the barrier, so therefore the slower the reaction rate. In general, at a given temperature, the higher the activation energy for a chemical reaction, the slower the reaction rate. Are there any way to speed up the chemical reaction? Increase the concentration of the reactant, which result in more collision per unit time. Increase temperature, which result in more collision per unit time, and also in high energy collision. So this both way can increase your rate. Now, in terms of the activation energy, you can use catalyst, which lowers the activation energy barrier, that also speed up the chemical reaction. The catalyst does not change the position of equilibrium, only how fast the equilibrium is reached. And here's the comparison for a chemical reaction with catalyst and without catalyst. So the red line is with catalyst. So you can see with catalyst, the energy barrier or the activation energy is much lower. It's only from this point here to this point here, compared to here to here. So therefore, the reaction, the same reaction with catalyst can go very, very fast, but the equilibrium position doesn't change, which means once you have the equilibrium, how much product you have, how much reactant you have. You see, with the catalyst, without the catalyst, you ending at the same place. Okay. And so enzyme in the biological system, like human beings and animals, so they are all use one use that like catalysts. Many reactants are thermally sensitive. Increase in temperature often destroys them. The only way to carry out many reactions is to use catalysts. So human body, you cannot use high temperature. Most of the thousands of reactions that must occur for living organism to survive will be too slow at normal temperature. So living organisms use enzymes, biological catalysts that increase the rate of biological reactions. And here is the energy diagram. Let's see for some of those chemical reactions use enzymes. So the enzyme sucrase creates a pathway with lower activation energy for the conversion of sucrose to glucose and fructose. So here's a picture for the sucrose. It's like glucose is uh, six atom ring here. Fructose is a 5 atom ring here. So usually you want to you have the human the living organism need to break this apart into glucose and fructose. Then they can go through the many other chemical reactions to use glucose to produce energy. So therefore to have this reaction happen kind of in a good rate, you want to use an enzyme called the sucrase. And here the comparison for the conversion of sucrose to glucose and fructose with catalyst, the red line, and without catalyst. Now, how enzyme work? That is very interesting and very interesting to study that. When sucrose is in the active site of the sucrase, so here the whole like the larger picture, the structure is called sucrase, which is the enzyme. Well, that's like kind of protein, and only one part of that called the active site is active. So it's kind of you have that model, you have the sucrose fit in, but try to imagine this structure is not rigid. You can kind of always like vibrate, a kind of a dough, change the shape, and always when the sucrose come in, it will change into that shape and fit in. So when sucrose is in the active site of sucrase, the bond between the glucose and fructose unit weakens, lower the activation energy for the reaction and increase the reaction rate. Okay, so this is end of this chapter 15.